Welcome to this next video in which we are discussing separable polynomials. Okay, so in this next video what I'm going to introduce is a really useful tool for being able to make more theorems about separable polynomials, namely the derivative of a polynomial. Now, you will have met the concept of a derivative of a polynomial before in analysis. However, the way we're going to define it here, although the formula is going to be exactly the same, the actual way that we define it is very different to the way that we define it in analysis. In analysis, we use limits and differentiation to define the derivative of a polynomial. Here, we don't have any concept of a limit. You need topology to have the concept of a limit. We don't have any sort of structure like that. So we're just going to define it using the formula, and the formula doesn't require differentiation or limits to define. Okay, so we are now going to define the derivative of a polynomial in an arbitrary ring of polynomials over an arbitrary field. Okay, so let's go then. So this is the way we're going to define it. So let's say we've got some polynomial f of x, which is in the ring of polynomials over a field capital F, and just to have an explicitly written out version of it, let's have it here. So f of x is equal to f0 is the constant coefficient, f1x plus f2x squared plus all the way up to fn xn, like so. Okay, so here is our polynomial f of x from the ring of polynomials over the field capital F. And we're now going to define the derivative of this polynomial. So the derivative of this polynomial, which we're going to denote like so, d, and then we'll subscript it x of f of x. And note the notation we're using here is very different from the notation that you would use in calculus or analysis. Okay, that highlights the fact that we are using this in a different sense to the way that it's used in analysis. Okay, we are making this as a definition, not requiring differentiation at all. Okay, so we're going to use this notation, capital D, and then subscript x for the derivative of the polynomial f of x, and we'll just call this the derivative of the polynomial f of x. Okay, so how is this defined? Well, the way you do it is exactly the way that you will have learnt in calculus long ago. For each of the terms in the polynomial, you just lower the power of x by 1, okay, and then multiply by the old power. So the constant term goes because that will be multiplied by 0 because it's in front of x to the power of 0. So you'll lower the power by 1. Of course, you don't even need to think about what you'd end up with there because you're going to then multiply by 0. So the constant term vanishes. For the degree 1 term here, you'll multiply by the old power, so you'll get multiplication by 1, and then you'll lower the power by 1, so it'll go to x0. So the degree 1 term will now just become the constant term, so you'll get f1 here. For the degree 2 term, you will multiply by the old power, so you'll multiply by 2. Now, of course, 2, it's an element of an arbitrary field, capital F. It's an element of an arbitrary ring, in fact. Okay? The way it's defined is it's just 1 plus 1. 1 is always an element of an arbitrary field, so you can add it to itself to get an element of the field, and that's the element that we call 2. So that's what we mean by 2. So 2 is just 1 plus 1. Okay? And you'll multiply the element 2 with the coefficient f2, and then you'll lower the power here by 1, so you'll get x to the 1, and then this will continue on all the way up to here. So you'll multiply through by the old power, which is n now, okay, and that's just 1 plus 1 plus 1 n times. That will multiply the coefficient fn, and then you'll lower the power here by 1, so it'll go to x to the n minus 1 here. Okay, so that then is how we're going to define the derivative of this polynomial. Right, so there's the formula. The first thing I want to show you is that this can be very strange if we're working in a field that has characteristic p. Okay, it's very intuitive. This will work perfectly intuitively if you're working in a field of characteristic 0. But if you're working in a field of characteristic p, or indeed, it doesn't need to be necessarily, well, sorry, yes it does. If you're working in a field of characteristic p, i.e. a natural prime number, then the derivative can end up being very strange. So that's the first thing that I want to show you, and then what I'm going to show you is two of the important rules that differentiation of a polynomial is going to obey, or rather the derivative of a polynomial is going to obey. I shouldn't call it differentiation because we're not using differentiation to define this derivative. Okay, oh, and I should probably just stress the fact that I did not ever need the notion of differentiation to define that. Okay, yes, of course, this is incredibly important in analysis, and it is what you get if you differentiate a polynomial in analysis, but you don't need analysis, you don't need differentiation to define that. That formula is perfectly able to be defined without differentiation, and indeed that's what we're doing here. That's the spirit of what we're doing here. We're just defining this to be the derivative of a polynomial, and it's perfectly definable with nothing more than what we've already got. Okay, right, so that's how we define the derivative of a polynomial then. So the first thing I want to show you is that this can be very strange if you're working in a field of characteristic a prime. Okay, so let's say that the field that you're working with is characteristic P. Now remember what the characteristic of a field actually means. It means the smallest number of times that you can add 1 to itself and get 0. So basically if you add 1 in the field to itself p times, you will get 0. Now why is that going to make the derivative of a polynomial in the ring of polynomials over this field of characteristic P strange? Well, remember how we define the derivative. We multiply by the old power. Now if that power is a multiple of p, then you will be multiplying your coefficient by a multiple of p, and that will just mean 1 added to itself a multiple of p times, and of course in a field of characteristic P that's going to equal 0, so that's why this is going to affect the derivative. Okay, so just to emphasize this, let's say we consider the derivative of, let's have a very simple polynomial from the ring of polynomials over this field capital F. We'll have some coefficient a, and then it will be in front of x to the power of p here. Okay, now if we were to actually find the derivative of this, what we need to do is multiply the coefficient by the old power. So we need to multiply p and a together, and then we need to lower the power by 1. So it'll go down to p minus 1. Okay, now p means 1 plus 1 plus 1 p times. That's 0 because we're working in a field of characteristic P. So you're multiplying by 0 here, so this coefficient is just going to become 0, i.e. the derivative of this is just going to become the 0 polynomial. So that's why the derivative of a polynomial in a field of characteristic P can be very strange. Okay, so you do need to acknowledge that if we're working in a field of characteristic a prime number rather than a field of characteristic 0, the derivative of a polynomial can be rather unintuitive. Okay, to take this even further, let's say that we have the derivative of, let's go for a x to the power of 3p plus b x to the power of 2p plus c x to the power of p plus, let's say, a constant term d. Okay, so a polynomial of this form where all of the non-zero coefficients are in front of powers of x that are a multiple of p, and then we've also got just a constant term here, then my claim is that that's going to be equal to 0 as well, because when we differentiate, well, I shouldn't say differentiate, when we take the derivative of this, we'll go through each term here and we'll multiply the coefficient by the old power. So in this case we'll multiply the coefficient by 3 times p, but of course that will be equal to 0, so this one will vanish. In this one we'll multiply the coefficient by 2p, that'll be equal to 0, so that one will vanish. In this case we'll multiply this one by p, so that one will go to 0 and that will vanish. And of course the constant term will also vanish when we take the derivative. Okay, so this entire polynomial, its derivative will equal 0. So beware that when you're working in a field of characteristic a prime, that the derivative of your polynomial might not be what you expect it to be. Okay, you can take some polynomials that you would think would not have derivative equal to the 0 polynomial, and when you do take their derivative you can find that you suddenly do get the 0 polynomial. If, as I say, all of the non-zero coefficients are in front of powers of x that are x to the power of a multiple of p. Okay, so that's my first warning with this notion of the derivative of a polynomial in a ring of polynomials over an arbitrary field, that it can be rather different from what you're used to from calculus. Okay, so what I now want to show you is the similarities of this with the way that we saw it in calculus. Okay, taking the derivative of a polynomial does obey two very nice rules which we need to be aware of to be able to use it in any useful way at all. Okay, and the two nice rules are that if you take the derivative of a polynomial f of x plus a polynomial g of x, where you're adding the two polynomials together in the ring of polynomials over the field capital F, this is equal to, if you firstly take the derivative of the polynomial f of x here, just give that a little bit of a curl there, the derivative of f of x, and then you add it to the derivative of the polynomial g of x, and of course this will still be addition in the ring of polynomials over the field. Okay, so that's one of the nice rules, and we'll prove that in just a moment, but I hope it should be an intuitive rule for this to obey. And then the other rule is the product rule. So if you take the derivative of the polynomial f of x times g of x, and again they're being multiplied together in the ring of polynomials over the field, this is going to equal the derivative of f of x times g of x, I'll put that round in brackets like that, times g of x, plus f of x times the derivative of g of x, like so. When I put an extra bracket in there, so I'll put one there. Okay, right. So this is obviously the familiar product rule from calculus, but we need to prove that both of these formulas work with regards to derivatives of polynomials over arbitrary fields. Of course, we know that these are going to be true if we're working with the field of real numbers. That's not a problem. But we need to prove that they still apply when we're working with the field, well, with the arbitrary field capital F. Okay, so that's going to be our job for the rest of this video then. Okay, so we'll start off with the easier one, and indeed we'll need the first one to actually prove the second one. So we'll start off with the fact that the derivative of the sum of two polynomials, f of x plus g of x, is actually the derivative of f of x, that's some polynomial in the ring of polynomials, plus the derivative of g of x, and again that will be some polynomial in the ring of polynomials over the field. Okay, so how are we going to prove that then? Well, we're just going to develop both sides. So let's bring this down here and try and prove that this is true. Okay, so firstly let's just write out explicitly f of x and g of x. So written out explicitly, this is the derivative of the polynomial f of x, and we'll write that as the sum over I fi x to the I here. Okay. Where of course only a finite number of these coefficients are going to be non-zero, and then we'll have g of x written out explicitly as the sum over I gi x to the I here, where of course this addition is in the ring of polynomials. Okay, so how then do we add these two polynomials together? Well, of course we are familiar with how we add two polynomials now in the ring of polynomials together. We add the corresponding coefficients that are in front of the same power of x together. Okay, so this will just become the derivative of the sum over I, and the answer to this is now you add fi to gi, and then you stick that in front of x to the power of I, and I'm just going to colour code the additions in here. So we have addition in the field capital F, and we're also going to have addition in the ring of polynomials over the field capital F, and we'll colour code those in different colours. So addition in the field capital F is here. When we're adding the coefficients, you add those together in the field capital F, and that's in orange there. We'll have addition in the ring of polynomials over the field in green, and this is of course addition in the ring of polynomials over the field, and so is this one here. Okay, so that is just applying the definition of addition of two polynomials in the ring of polynomials over the field. Now what we can do is apply the definition of the derivative of our polynomial here, and we know what we have to do. All we have to do is go to all of the monomial terms, multiply by the old power and lower the power by 1. Okay, so this will now become the sum over I of I times f of I plus g of I, where of course this is now multiplication in the field capital F. So I will just put a orange dot there, and let me just straighten this up a little bit. So we'll have an orange dot here for that multiplication in the field capital F, and we'll have an addition there in orange as well, and this will now be in front of the power of x to the power of I minus 1 there. Okay, so what we are now trying to prove then is that this thing here is the same as what we would get from doing this. Now, hopefully it should be reasonably intuitive that that is the case, but let's just work this right-hand side out to explicitly show that. So the derivative of f of x, so we would write f of x explicitly out as the sum over I of fi xi, and then we take the derivative of that, and of course that would become the sum over I of I times, and there will be a multiplication in the field capital F, fi, all in front of x to the power of I minus 1 there. Okay, so this is multiplication in the field capital F, and then you'd still have the plus here, so this is an addition here, and that will be an addition in the ring of polynomials over the field capital F, so I'll put that there. So here's the addition, and we'd be adding it to the derivative of g of x, which would be the sum over I times in the field gi x to the I minus 1, like so. Okay, and again that's multiplication in the field capital F, so I'll colour that in orange. Now, of course, if you were to add those two together, you would do it component-wise, and of course you would end up with this thing here. You just factor out the I there and get it like so, applying distributivity in the field capital F. Okay, so that's the reason that addition does indeed obey this nice rule, and of course once we've got that the derivative of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x, we can then extend this to an arbitrary string of polynomials added together. So we could have the derivative of f1 of x plus f2 of x plus all the way up to fn of x, and that would end up being the derivative of f1 of x plus the derivative of f2 of x plus all the way up to the derivative of fn of x. Okay, so once you've proven that addition obeys this beautiful rule for two polynomials being added together, it's very simple to extend that up to it being an equivalent rule for the derivative of an arbitrary finite number of polynomials added together. Okay, right. So now what we're going to turn our attention to is the slightly more complicated one to prove, which is the product rule here, but it's still not that difficult to prove. And I want to stress how different what we are doing here is from the proofs that you would give of these results in analysis. In analysis, you prove this for arbitrary functions, f of x and g of x. Here we're just doing it for polynomials, which is why these proofs are much simpler than they are in analysis. Okay, as I say, in analysis you would do it for much more general functions, not just polynomials. We are just doing it for polynomials, and we only care about polynomials. We do not care about e to the power of x. Okay, that is not something that is of interest to us in algebra. Okay, so we are just proving these results for polynomials, in case you're just questioning why we are able to prove these so easily when in calculus in analysis they require more substantial proofs. Okay, so let's now do the product rule here. It's because the answer, which I don't know if I explicitly stated it, is because we are just doing it for polynomials, not arbitrary functions. Okay, so now let's prove the product rule here. So first thing I'll do is I'll just write it out with the explicit versions of the polynomial f of x and g of x here. So we want to prove, and I'll move this up now, that the derivative of the polynomial f of x, which is the sum over I fi x to the I here, multiplied in the ring of polynomials over the field with the sum j gj xj, which of course is our polynomial g of x here. So this is multiplication in the ring of polynomials over the field, so I'll colour it in green there. We want to prove, and I'll just straighten this back up, that this is equal to the derivative of this one, and I'll put a little question mark here, the derivative of the polynomial f of x, sum over I of fi xi, times the polynomial g of x, still in the ring of polynomials over the field f, so this is the sum over j, and I'll keep the indexes separate here, gj x to the j, okay, and I'll colour that multiplication in there in green because that's still multiplication in the ring of polynomials over the field capital F. And then we want to add this to, and we're performing this addition in the ring of polynomials over the field F, to the polynomial f of x, sum over I, fi xi, multiplied with the derivative of the polynomial g of x, so the derivative of the sum over j, gj, x to the j here. Okay, and of course this multiplication here is in the ring of polynomials over the field capital F. Okay, right, so we want to prove that this is true. So how are we going to do this? Well, our normal tactic, we'll just develop this side, and show that they equal one another. Okay, so we'll start once again with developing the left-hand side here. So the first thing then that we need to do is multiply these two polynomials together. Now, how do we multiply two polynomials in the ring of polynomials over the field? Well, we're very familiar with this. What we do is we imagine splitting our polynomial down into a monomial decomposition. Okay, so imagine going from thinking of these sums as just being metal sums, i.e. they're just symbolic sums where you've just got, you know, the powers of x are just placeholders. You've put coefficients in front of each of the powers of x from your field capital F, and then you've stuck these plus symbols in between the terms just to create a symbol. We go from thinking of the polynomial in that way to actually thinking of the monomials as being separate polynomials with the pluses in between them as meaning pluses in the ring of polynomials. Okay, and we do the same here. So we think of decomposing a polynomial into its sum of monomials, and then of course we know that we have defined multiplication of two monomials, and the way that we define multiplication of two monomials is you multiply the two coefficients together in the field capital F and you add the two powers of x. Okay, and now since we've got this expressed as a great big sum of monomials and we're multiplying it by another great big sum of monomials, we can then just apply the fact that we want distributivity to be true in our ring of polynomials over the field capital F, and there's only one thing that this can then actually be. Okay, so it'll become the sum over I, the sum over j, where both of these sums are actually in the ring of polynomials over the field capital F, so I will underline it in green to denote that they're actual additions in the ring of polynomials over the field F. And then you've got all of the monomials here multiplied by all of the monomials here, so you'll get fi times gj, okay, where that multiplication is done in the field capital F, so that's an orange multiplication there. And then you'll add the powers of x, you'll have x to the power of I plus j here. Okay, so that's the product of this polynomial f of x with this polynomial g of x, and we're then going to take the derivative of that. Okay, so that is the left-hand side developed a little bit, and let's now actually take the derivative of this. Now note, what we've got here is not the polynomial in its raw metal symbolic form. Okay, we have actually got a sum of monomials here that you would actually have to work out if you wanted to find the final answer. This is not the final answer as to what this multiplied by this is. This is a bunch of monomials that we'd have to sum together to get the final answer to what this polynomial multiplied by this polynomial is. Okay, so this is a real sum in the ring of polynomials over the field, and luckily we know that it's going to be a finite sum because only a finite number of these are going to be non-zero, so you've only got a finite number of monomials here to actually add together. And we know that differentiation works very nicely with sums in the ring of polynomials over the field. So what we can actually just do is bring the derivative inside here, okay, using this rule here that you can either firstly sum and then differentiate, or firstly differentiate and then sum. At the moment we're firstly summing and then differentiating. We're now going to change it around so that we firstly differentiate and then sum. Okay, so we'll bring the sum over I, sum over j out, and that's still summation in the ring of polynomials over the field capital F, and we're then going to differentiate each of the monomials here. So we're going to differentiate these monomials, fi times gj, x to the I plus j. Okay, and all of these are little polynomials in their own right, basically. So of course we know exactly how to differentiate a monomial in this way. You multiply by the old power and lower the power by 1. Okay, so this is then going to become the sum over I, the sum over j of, and then we'll have I plus j, okay, times fi times gj, okay, where that's multiplication in the ring, in the field capital F, and then we'll lower the power of x by 1, so it'll become x to the power of I plus j minus 1 in this way. Okay, right, so now what we want to do is show that if we play with the right hand side here, we're going to get the same thing as we get here. Okay, so let's play around with this side a little bit. What we need to do is get an expression for both of these two things that we're adding together here, and show that if we do add them together, what we'll get is here. Okay, so let's firstly do this one here, the most logical one to start with. So the derivative of this polynomial, we know what that's going to be. That's going to be the sum over I times fi x to the I minus 1 here, where this is multiplication in the field capital F, so I'll colour that in orange. Okay, and we then need to multiply this polynomial, which is the derivative of f of x, with the polynomial g of x, which is the sum over j, gj, x to the j here. Okay, so that multiplication is multiplication in the ring of polynomials over the field capital F. What we then need to do is the same thing here, so we'll get that this needs to be added to in the ring of polynomials over the field. The polynomial f of x, we do nothing with that, so we'll leave that as it is. Sum over I, fi, x to the I here, and then we want to multiply that with the derivative of this, which of course is just the sum over j times gj, x to the j minus 1, like so, where this is of course multiplication in the ring of polynomials over the field, so it needs to be in green, and that multiplication in there, which I haven't actually given an explicit multiplication symbol for, but the j times gj, that's done in the field capital F. So how are we going to get this closer to this? Well, of course we need to multiply this with this and multiply this with this, so the way that this is going to work is exactly the way that we multiply two polynomials here. You view splitting this down into a monomial decomposition, and you view splitting this down into a monomial decomposition. Absolutely fine. Okay, this is just a polynomial, you can split it down into its monomial decomposition. This is just a polynomial, you can split it down into its monomial decomposition. Okay, in addition we can split that down into its monomial decomposition and that down into its monomial decomposition. Then all we need to do is take the great big sum of all of the monomials here, multiply by the monomials here, and do that again for this one here. Okay, so this is going to become then, so firstly this one here, we're going to get the sum over I, the sum over j, and then we need every monomial here multiplied with every monomial here. So we take the coefficient here, multiply it with the coefficient here, so we'll get I times fi times gj. Now of course multiplication in the field is associative, so I won't bother putting brackets in there. So we've got I times fi times gj, and then we'll have all of that in front of x to the I plus j minus 1, so just writing that rather than putting I minus 1 plus j, of course we know that will be I plus j minus 1. So that's absolutely fine, and this of course is still, these sums are still sums of the monomials that you've got here. Okay, so again, this is not the final answer, this is a sum of monomials that you can actually perform in the ring of polynomials to actually get your final answer. And this is going to be added to a similar thing for this. We'll get the sum over I, the sum over j, and then we want all the monomials multiplied together, so we'll get j times gj, that's not so obvious that it's a j, but it is a j there, times fi, so we might as well put the j at the front, because of course multiplication is associative and commutative, so I can move things around, and then we'll get j times fi times gj, like so, in front of x to the power of I plus j minus 1 again, so just adding the powers of x together. And again, this summation, all these summations are just going to be in the ring of polynomials once again, and that plus in between these is also going to be in the ring of polynomials. Okay, but the multiplications here are in the field capital F. Okay, so then finally what we need to do is add these two together, and of course we just have a great big sum of monomials here, we have a great big sum of monomials here, we're then just adding one great big sum of monomials to another great big sum of monomials. How do we make this tidier? Okay, well let me just highlight that up there to sort of show the parallels here. Remember, this is a great big sum of monomials as well. I just forgot to colour it in green. So how can we make this tidy? Well, what we can do is we can get things that have the same power of x close to one another. So if we've got x to the I plus j minus 1 here, and we've got x to the I plus j minus 1 here, we can get those two corresponding terms where the i's and the j's are exactly the same. When I should say, yes, we're assuming what I'm going to do is I'm going to get monomials that are in this sum which have the same I and the same j close to one another, not the same power, okay, because there might be other monomials just in this sum, for instance, that have the same power of x even though they aren't the same I and the same j. So I'm bringing monomials from here that have the same one I and one j, a certain I and a certain j, next to the equivalent one from over here, if it exists. If it doesn't exist, if it's just 0, then obviously don't bother. But if you do have a monomial here which has a certain I and a certain j, and there's a corresponding one over here, you bring the two close together, okay, and then we can factor out the x to the I plus j minus 1, okay, and then add these two things together, add the two coefficients. So just performing obviously the way that addition works in the ring of polynomials over the field capital F, you just add the corresponding coefficients. Okay, so we can simplify this, I claim, into this, because of course what we can then do is pull out, when we've got this added to this, we can pull out the fi times gj like so, and we'll end up with I plus j exactly like so. So we're just bringing terms that have a certain I and a certain j here next to their corresponding term from here. Okay, you're adding those two together in the way that you do in the ring of polynomials over the field capital F, and what you'll get is this, where you've got the I plus j added together in the field capital F multiplied by fi times gj in the field capital F. So truly this does become equal to this. So we can now tick off the product rule here as being true. Okay, so in an arbitrary ring of polynomials over an arbitrary field, if you take the derivative of the product of two polynomials, then that is the derivative of the first polynomial times the second polynomial unchanged, plus the first polynomial unchanged times the derivative of the second polynomial. The product rule does indeed hold true. Okay, so that's an introduction to this incredibly powerful tool of the derivative, and in the next video what we will do is apply the derivative of a polynomial to actually understanding separability further.